Welcome, friends. This is the fifth video of the business statistics course, and we were in module 2. In the previous video, we discussed binomial distribution, and in today's video, we are going to discuss Poisson distribution. So, earlier, I mentioned that there are two types of discrete distributions that we are going to discuss here. The first one is binomial, which we have already discussed in the previous video, and now this is the time for discussing Poisson distribution. And therefore, like we did in binomial, in this case also, we will see what are the underlying stories for a Poisson's distribution. So first of all, in case of Poisson's distribution, suppose any problem is given to you, so how will you identify that it is related to Poisson's distribution? For that, this story is very important. So note this just point by point. Something is appearing at an average rate of lambda. Okay, so something is appearing. What can appear? So a defect can appear, an accident can appear, or customers coming in a queue, customers can appear, or any other thing that can appear. For example, earthquake can appear. So all those things that can appear. So this is the first point. Something is appearing. And then at every moment, there are two possibilities. So either appear or not appear. So for instance, if there is a defect, then either the defect will appear or it will not appear. So nothing else can happen. So there are two possibilities. Either it will appear or it will not appear. So then what is the third point? Third point is, what do we want to achieve? So we want to find the probability of appearance for a certain number of times for a time span. What does that mean? So for example, if a defect is appearing at a particular rate of lambda, ठीक? So this defect rate is lambda, then what is the probability that a certain number of defects will appear for a given time span t? So that is the problem we are trying to solve. And from there, it is very important to define the unit of lambda. Why? Because here you see in the question itself that we are going to solve contains a time span. So we are not trying to find the probability of appearance for a certain number of times. We are not stopping here. We are not stopping here. We are further extending this question that for a particular time span, for example, 1 hour or 1 minute or whatever, within that time span, how many defects, n defects will appear? What is the probability of getting n defects within that time frame? And so, therefore, when we will write lambda, lambda should be in terms of this time span. So, for example, if lambda, suppose lambda is given in per hour. Just a minute. Okay. Lambda, suppose lambda is given in per hour. Okay. But suppose the question is asked that what is the probability of appearance of suppose 3 defects in 1 minute. So you can see here that although lambda is given on a per hour basis, our question asks it in terms of 1 minute. That means these two are not matching. These two are not matching. So therefore, in all those cases, you will convert lambda in this term, that means in 1 minute. So for example, if lambda is given in per hour, then you will first convert lambda into per minute and then calculate everything else. But if these two are matching, for example, if it is given in per hour and the time span also asked is per hour, then there is no problem. You don't have to convert lambda into any other unit. The same unit of given here, the same unit given here can be used to calculate every other thing. So that is the thing. So the Poisson random variable following a Poisson distribution will have only one parameter, which is lambda. So unlike binomial, we have seen already in binomial that we had two parameters n and p, but in case of Poisson distribution, we only have one parameter, that is lambda. So like binomial distribution, we have already developed our table for Poisson distribution also. So for example, x taking the values of x1, x2, x3, etc. and the corresponding PMF, this is the PMF, and this is the CDF. So the PMF can be calculated using this formula, lambda to the power xi into e to the power minus lambda divided by xi factorial, or otherwise use this Poisson distribution Excel formula, which is directly which can be used to calculate this PMF values directly. And for CDF, either use the fundamental principle of adding these uh, PMFs, like for example, fx1 is equal to px1, and then fx2 is equal to px1 plus px2, fx3 is equal to px1, px2, px3, uh, like this way. Or otherwise, you can use this Poisson distribution cumulative distribution function formula directly using Excel. So now, without wasting any time, we will move on to our Excel sheet to implement these relationships using uh, an example. So let us move on to the Excel sheet. So here is the problem. In a particular city road, 60 accidents happen in a year. I know this is a morbid figure. 60 accidents never happen in a year, but let us assume that it happens. Then a traffic police is watching the movement on the road for a day. Then what is the probability of having xi number of accidents? Accidents in a day again. So therefore, as I was mentioning in the slide, you see the two units clearly. First of all, lambda is given. So you can see that the lambda value is given in per year basis. That means 60 accidents in a year. But our time span is 1 day. So therefore, we cannot write lambda as 60 here. So we have to write lambda in terms of accident per day. And so assume that 1 year is equal to 300 days, and then divide 60 by 300, so that 0.2 accidents per day should be our lambda, which can be entered here in the formula for PDF and PMF and CDF. And so then implement this 0, 1, 2, 3, 4 is the value of x. That means these are the xi value. So using algebraic formula of PMF, this one, px is equal to lambda to the power x into exponential of minus lambda divided by factorial of x. So this gives you the PMF values, and how to calculate the CDF values using fundamental relationship. This one is equal to this, then this is plus this. Just add this cumulatively to get the CDF values. Okay, and then if you want to calculate the values using the Excel function directly, then use Poisson distribution, then xi, then your lambda, and then 0 if this is PMF. If this is PMF, then 0. Otherwise, 1 for CDF. So I will copy this, and you can see here both these values are matching. These PMF values are matching with these PMF values, and this CDF is matching with this CDF. So anyway, in either you use the algebraic formula and fundamental relationship to calculate PMF and CDF, or otherwise you can use the Excel PMF and Excel CDF functions directly. Both are correct. So now very important thing is we need to discuss similarities and differences between binomial and Poisson distribution, because I will show this in the slides. If you can check that both are very similar in certain aspects, then there are subtle dissimilarities also. So we will discuss that. So let us come to the slides once again. So let us try to see the binomial and Poisson distribution point by point. So first of all, note that when we were discussing binomial distribution, then we had exactly two outcomes: true, false, or 0, 1, success, failure, like that. Exactly two outcomes were possible. When we are actually discussing Poisson distribution, then also we only have two outcomes. How? Defect or no defect, accident or no accident, right? Customers either coming in the queue or they are not coming. So in case of binomial as well as in case of Poisson, so both are having two outcomes, right? Then you see there are two parameters in binomial distribution. One is your P, that is the probability of success. Probability of success, right? And in case of Poisson distribution, you have lambda, which is rate of appearance, right? Are they really different? Probability of having success and rate of appearance, are they really different? I don't think so. Please think about this. Probability of success and rate of appearance, both are same thing. We have already discussed this, that two outcomes are possible: appearance or no appearance in case of Poisson distribution, right? So if these two outcomes are possible, then we are talking about rate of appearance. Rate of appearance. Then is it not same that it is same as probability of appearance? And hence these two are same. So two things are same, two outcomes and probabilities. Now, in case of binomial distribution, we are doing this experiment for n times. Okay, and therefore we had another parameter n. But in case of Poisson distribution, we are not doing it n times or anything like that. In the situation is little different. We are doing this, or actually checking this, for a particular time span, which is t, for particular time span, and we are writing lambda in terms of this time, and therefore it is not a separate parameter as such. So we have incorporated the effect of this time, this t, inside lambda, because we have defined lambda in terms of t, in terms of that time span. I have already discussed this in the previous slide. So therefore there is no need to separately identify another parameter. for Poisson distribution. So do you understand this? Please think about this and repeatedly listen this. I am telling you that in case of binomial distribution, we had another parameter which was n, which is the number of times the experiment that has to be repeated. But in case of Poisson distribution, we don't have any kind of n. Rather, we have a particular time span for which we want to answer the question that for that particular time span, what is the probability of getting the defect for certain number of times, right? So then, but we don't have to define t or this time span as a separate parameter because we have already incorporated its effect within the definition of within the very definition of lambda. Okay, so having said that, can we uh, solve the previous problem using binomial distribution? So we had already created the PMF and CDF using Poisson distribution, but can we actually use binomial distribution for the same problem that we have discussed right now? So let us try to do that in Excel again. So this is the same Excel sheet. We are trying to solve this problem using binomial. So do we have these parameters with us, n and p? I right now discussed in the previous slide that we have p is equal to lambda actually. P is nothing but lambda, right? P is the probability of success in case of binomial distribution and lambda is the rate of appearance. Both are similar. So in case of P, you can use the same lambda value. Okay, this point 2. But then what is n? We don't have any n here. Hmm? How to identify n? Yes, we do not have any n. But you see, the problem or the functionality of Poisson distribution is such that there is no upper bound for the xi values. So for example, you can start from 0, x equal to 0, then x equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever x value you can use. There is no limit to that. But that is not true for binomial distribution. Suppose you, if you have n is equal to 5, suppose, then x cannot be more than 5, right? You are, suppose you are tossing a coin, you are tossing it 5 times, then number of times heads can occur cannot be more than 5, right? So it can, the value of x cannot be greater than n. So that is one thing, another difference with binomial and Poisson. So remember that. So then again, so what should be the value of n in this case? See, it is true that the x value, the upper bound of the x value is unlimited for Poisson distribution. But actually, if you see the PMF values, after 4, is it something very different from 0? It is very close to 0, right? So maybe we can assume that 4 is the upper bound so that we can use n is equal to 4 here in case of binomial distribution. I mean, but not binomial distribution, the comparison of Poisson with binomial for this problem. So we didn't have any n values given for equivalent binomial distribution. We just figure out that for x equal to 4, the PMF of Poisson is so small that for x equal to 5, it will be like 0. So n cannot be more than 4, or you can take 5 also here. So I think this is clear. So then you can calculate the binomial PMF. So we use the binom dist formula equal to binom dist numbers is your x, trials is n, then probability is p, and cumulative. Is it cumulative distribution function? No, it is probability mass function, therefore false. That means 0. So here is your binomial, equivalent binomial PMF. But see, are these values really matching? This is 819 and this is 328. This is 164. This is 40410, something like that. So are these values really matching? I don't think so. So therefore, is it so that Poisson and binomial cannot be compared? Yes, actually it is so only when your p value or this lambda value are larger. You see here, what is the p value? P value is zero point 0.2, which is much higher. 0.2, 60 accidents per year. This is a humongous figure. This cannot happen. When this type of figure is available, then your Poisson probabilities and binomial probabilities will never match. Only when the value of the lambda is too thin, like 1 accident per year or 3 accidents per year. Suppose this is 3 accidents per year, so then this is 3 by this, so 0.01, right? So now are they matching? They are trying to match. See, 0.99, 0.95. Let us reduce this once more. So for example, this is 1 accident per year. Now 9998. These are all some matching. Suppose this is 0.5 accidents per year. Then what? 998, 991. Now they are like matching. So always remember, when the Poisson probability, that means the rate of appearance, lambda, is small, it has to be very small in order to approximate that in terms of binomial distribution. Otherwise, you cannot use binomial distribution for Poisson. That will give you error in your results. Okay. So this is one important point that you need to remember. So there is actually, it is very convenient to see this in actual problems, because when you solve actual problems in case of binomial distribution, the p and 1 minus p, these two values are close enough. For example, p will be 0.2, then this will be 0.8, then mm, p will be 0.5, this will be 0.5. Like the p and 1 minus p distribution will be not too much difference. But if you solve problems like Poisson distribution, then the probability of appearance versus the probability of non-appearance. So probability of appearance and then probability of non-appearance. This will be much difference. For example, probability of appearance will be 0.002, and then this will be like this. Then only you should use Poisson distribution. And then also, if you approximate that using binomial PMF, that is absolutely fine. Then it will giving you almost similar results. So that's it about Poisson distribution. Now, like binomial distribution, you can calculate the different answers. For example, what is the probability of having 3 accidents per day? What will be that? It is simply this one, PMF of x equal to 3. Then, for example, probability of less than 3 accidents per day. What will be that? This will be these three, x equal to 0, 1, and 2. Then what will be probability of having more than 1 accident per day? This will be 2, 3, and 4. The sum of these three. like that. In this way, you can calculate these probabilities. We have discussed these things in binomial. This is not a big deal. You can do that yourself. So that's all about Poisson distribution. I hope you have understood the concept and how to solve the problems. If you have any doubts, you can use the comment section to inform me. Otherwise, this is all from my side as far as the Poisson distribution is concerned. So let us meet in the next video where we will discuss the exponential distribution. Thank you for watching this video.